Now we'll just summarize again what we learned in the last video. Here are three bodies A, B and C, and we have drawn their displacement time graph. If you look up at the body B, by now you will know this is the graph of a body at rest, because the position or the distance is 6 meters throughout. If you look at body B, here the displacement is increasing uniformly. So this is a body with uniform speed. Uniform speed, or we also call it uniform motion. And the last body C, also the displacement is increasing but not uniformly. It's a curve. So this is non-uniform motion, where the speed is not constant. Speed not constant. So these are the three kinds of graphs that we have learnt of displacement time. So I just go over it again. Your body A was at rest. The body B was in uniform motion. And the body C was in non-uniform motion. Non-uniform, unequal distances, covering of unequal distances in equal intervals of time. Now let's examine the velocity time graphs. I've drawn 4 different graphs which tells us 4 different stories. Let's get on with object A. Now if you see in object A, it is moving here straight like this. Have you seen? Along the straight line. It's parallel to the x-axis. The velocity does not change. It remains 7 meters per second throughout. So we can say for this object A, it is with uniform velocity. It is a moving object. It has a velocity of 7 meters per second. Uniform velocity, and because the velocity is uniform, does not change, we say acceleration is 0. Look at the body B. Here again the velocity is increasing. So the velocity is changing. It is an accelerated motion. But however, here the acceleration or the velocity changes uniformly. So we say in this case it is uniform acceleration, because the velocity is changing by equal amounts in equal intervals of time. Now let's look at the object C. Here also the velocity is increasing, but it is not a straight line. It's increasing along a curve. So there is acceleration. The velocity is increasing, but not by equal amounts in equal intervals of time. So this is called non-uniform acceleration. The velocity increases by unequal amounts in equal intervals of time. And look at the last one, D. If you see D, here also the velocity is increasing uniformly. But there is one thing, the body hasn't started from 0. Have you seen from where the body has started its motion? It has started its motion from 4 meters per second. So this is an object that has not started from rest. It has started from 4 meters per second. What is the difference between B and D? Observe B. B starts from rest. Look at B. It has started from here. It has started from rest. But if you go at D, it has not started from rest. It has started from here. It had an initial velocity of 4 meters per second. So we were to summarize again, we would say A. For A, acceleration 0, uniform velocity. Then we get on to B. And for B, we will say uniform acceleration. Then we get on to C. Here we say non-uniform acceleration. Then we get on to D, which is also uniform acceleration. but body is not at rest. Body does not start from rest. In B, here, in B, this body starts from rest. So these are the different graphs. So graphically, we can represent all these different motions. Let's observe this graph again. It's an interesting graph here. So here we have an object first starting from rest. It goes along, the speed keeps on increasing. Hence we can say it's positive acceleration. Then it reaches at this point, and now the speed remains constant at 5 meters per second. And now at this point it starts dropping. The speed keeps dropping. By the time it is 30 meters per second, the acceleration, the velocity has become 0. We'll call these points A, we call this B, C and D. Now let us see what happens along AB. For at A, when we start, here's the velocity, this is point A, and at this point the initial velocity, which we say u, is 0 meter per second. So I'm going to write here, initial velocity is always written as u, which is 0 meter per second. Then the velocity keeps increasing. Here have you seen the velocity keeps on increasing till we reach the point B. At this point B, now what is the velocity at point B? If you see, we call it the final velocity, and that is 5 meter per second. See, this is the velocity at B, 5 meter per second. So V, final velocity, 5 meter per second. How long has this taken to change the velocity from 0 to 5? See here, we look at the time axis. So here this was time for B, and this is the time for A. So what is the time difference here? The time was 10. This is the time difference. This gives us the time difference here. This. So this is 10 minus 0, and that is 5 seconds. So it took 5 seconds for the velocity to change from 0 to 5. So what would the acceleration be? V minus u over t. We saw the v was 5, the u was 0, and the time was 5. So the acceleration is 5 over 5. So the acceleration is 1 meter per second square. So along AB, the acceleration was 1 meter per second square. Now we'll study the motion along BC. From B to C, let us see what happens. So at B, we have, this is the point at B here, and this is the point at C. Now at B, the velocity we saw, see, this is the velocity at B. The velocity is 5 meter per second. So we'll write here at B, the u, initial velocity, 5 meter per second. And when it reaches C, see, the velocities remain same. It's a straight line, horizontal line. At V also, which is the final position, it is also 5 meter per second. So 5 meter per second. How long has this change taken? At B, what was the time at B? We do this. This was the time at B. What is the time at C? We go down here. What is the time at C? 20. So the time for this would be 20 minus 10, and that would be 10. So when we want to calculate acceleration, it will be V minus u over t. We see the V is 5 and the u also is 5, and the time here is 10. And so we do this calculation, the acceleration becomes 0 meter per second square. And hence it is written here, have you seen, 0 acceleration. Why 0 acceleration? Please observe, the velocity has remained same, 5 meter, 5 meter. The body is moving with a constant velocity. There is uniform motion here. Now let's look from C to D. So here is C. We'll mark this here C. And then at c, what is the velocity at c? It is the initial velocity here at c is 5 meter per second. Have you seen at c? This is the velocity at c here. And then the body reaches d, which is the final point. And the final velocity here at d, see what is the final? Let's go back to the velocity here in c. It is 0 meter per second. The body has stopped moving. So from c to d, the initial velocity is 5 meter per second. The final velocity is 0 meter per second. So here the body from c to d has decreased. The velocity is decreasing. It is slowing down. How long has it taken to do that? At c, what was the time at c? This is the time at c here. This is the time at c. And this is the time at b, at d. So what is the difference in time? This is the difference in time between c and d. So here the time will be 30, which is at d, and 20. So this is 30 minus 20, and that is 10 seconds. So if I want to find acceleration here, v minus u over t, and that would be, iv is 0, see this is 0, minus u is 5 over time 10, and it is minus 1 by 2 meter per second square. Why did I get this negative sign? Because this is negative acceleration. This is retardation. Look, negative acceleration. The velocity is decreasing. This is retardation. So if I were to examine, just go over this graph again. The body starts at rest and it keeps on increasing its speed here. Once it is this position, then the speed remains constant, so we call it zero acceleration. Here in the first case we call it positive acceleration because the speed increases, and now the speed begins to decrease here. The body begins to slow down, and hence we call it negative acceleration. Now in which portion will you have uniform motion? Here will be uniform motion. In this region you will have uniform motion because the acceleration is 0. In this region you will have uniform acceleration, and here also uniform retardation.